Good afternoon, ladies and gentlemen. My name's Bruce Keith. I'm the President-elect of the Chartered Institution of Water and Environmental Management, and I'm also co-chair of the working group here at the FIG conference in Christchurch, New Zealand, looking at water as a natural resource and one which needs management. Mother Nature is a powerful force, on occasions for destruction and resulting in tragic loss of life. Such was the case here in Christchurch in South Island, New Zealand in 2010 and 2011, when a sequence of earthquakes wreaked havoc on this city and its hinterland. These events, all too frequent occurrences around the world, are also marked by commitment, fortitude and resilience, which are testimony to the very best hallmarks of human nature. Very quickly following a disaster, there's a human need to take stock of what has happened, assess the extent of the damage, and muster the resources, human, physical and financial, to rebuild. When disasters like the earthquake in Christchurch do occur, we realise that the basic services we take so easily for granted, particularly in the developed world, are no longer available. These include drinking water, sewerage and drainage infrastructure, hidden from view to most consumers, but essential to maintaining a healthy and vibrant community. This afternoon, I'm delighted to introduce a series of presentations on the earthquake's aftermath from 4 expert speakers who are actively involved in the projects they will describe. This session is organised by CIWEM members in the institution's New Zealand network. Several CIWEM members have been and remain actively involved in the response to the earthquakes. Other CIWEM members came to Christchurch specifically to work on the Christchurch recovery in SCIRT or the various consultancies. Some have remained here, others have returned home with the valuable skills they have learnt in Christchurch in the design, planning and building of the new infrastructure for the city. The Chartered Institution of Water and Environmental Management, CIWEM, is the leading chartered professional body for an integrated approach to water, sanitation, environment and sustainable development. The institution is independent, it's a qualifying body with a royal charter, a learned society, global and the natural home for professionals who care about the environment. The institution has 3 objectives: to advance the science and practice of water and environmental management for the public benefit, to promote education, training, study and research in that science and practice, again for the public benefit, and to publish the useful results of such research. And thirdly, to establish and maintain for the public benefit appropriate standards of competence and conduct on part of the members of the institution. It's my privilege to be the institution's President-elect. It's also my privilege to be here today to introduce the CIWEM presentation on the Christchurch earthquake and the recovery programme. I am delighted this afternoon to introduce Ian Macbeth, who will introduce the 4 speakers. I would also like to thank Becca and Opus, 2 leading firms of environmental engineers who are generously sponsoring this session at the FIG conference and the video, which will allow the knowledge transfer to a much wider audience.
Thank you, Bruce. Right, it's my pleasure to introduce the 4 speakers for today's final session. All are colleagues of mine at Becca. My name's Ian Macbeth and I'm the manager of the Christchurch Water team at Becca in Christchurch. Before introducing the speakers, I'd just like to put their presentations into some context for you. All 4 presenters and I live in Christchurch. We were living in Christchurch at the time of the earthquakes. Now, having grown up in Christchurch myself, I knew that other places in New Zealand around the world had earthquakes. I also knew that Christchurch didn't have earthquakes. So the events of late 2010 and 2011 were nothing short of terrifying initially and have been life-changing ever since. Not only were we working in a completely new environment for which we were almost completely unprepared, we were also living with our own domestic issues of broken homes, lack of facilities, traumatized families, and dealing with insurance companies. Working for an engineering consultancy like Becker, the earthquakes provided a career-defining opportunity to be involved in the rebuild of a city on a scale rarely seen anywhere in the world from one generation to the next. It's been a hugely exciting and emotionally challenging time to be here. These 4 papers showcase some of the work in which we've been involved. First up, we have Mark Christensen. At the time of the earthquakes, Mark was the water and waste manager at Christchurch City Council. He was responsible for all of the city's water network, as well as the sewage system and the wastewater treatment plant. With around 50 kilometres of water pipes damaged and 500 kilometres of sewers damaged, along with extensive damage to the wastewater treatment plant, he had an enormous responsibility for such a critical element of the city's well-being. Since 2014, with the repairs well underway, he's been at Becker, working out of our Christchurch office in a trans-Tasman role as a business director in our advisory services team. His paper looks at some of the key lessons learned from the post-earthquake repairs carried out at the wastewater treatment plant. Dave Hyler's next up, Senior Technical Director of Water Infrastructure in the Christchurch Water Team. Now, between 2011 and 2014, Dave was seconded into the Stronger Christchurch Infrastructure Rebuild Team, or SCIRT. He was in an asset assessment role at that time. His paper discusses a novel whole-of-life costing methodology that he and his team developed to evaluate rebuild options. Notably, this methodology can be applied anywhere subjected to natural hazards. Then we have Amber Murphy, an environmental engineer in the Christchurch Water Team as well. Having started her working career in Becker in 2010, she worked in one of the 4 design teams at SCIRT between 2012 and 2014. Her paper examines the repairs to the city's wastewater and stormwater drainage systems, not least dealing with the effects of up to a metre of ground settlement on gravity drainage in a flat city, as well as building resilience into those repairs. Finally, we have Greg Offer. He's a Senior Technical Director of Environmental Engineering in the Christchurch Water Team in Becker. Becker's had a contract with the Christchurch City Council since mid-2008 to provide professional services at the city's wastewater treatment plant. Greg's led our work at the plant throughout. The earthquakes brought a huge amount of disruption to the treatment processes, and his paper examines the initial response and then the subsequent challenging design and repairs to one of the key elements of the treatment process. So I'll now invite Mark Christensen to come to the lectern as the first of the 4 papers, and they'll follow on from each other with questions at the end.
Thank you, Keith. Thanks, Ian. So, as mentioned, earthquakes are fairly devastating events. You can turn a beautiful looking city like this into one that's not so pretty in about 45 seconds. So it was quite a devastating event on the 22nd of February. Magnitude 6.2 quake, not big by world standards, but it was shallow and close to the city. And that's coupled with the ground conditions resulted in huge damage. There's been about 14,000 aftershocks since the main quake, and occasionally we still get a reminder in the city that we're still a seismically active area. So what happened to the services? So working through them in I guess order of importance. Water supply pipes. So the map up there, the red dots there illustrate the number of breaks that were recorded around the city immediately after the February 22nd earthquake. We had about 30,000 homes without water supply, which is about 60,000 people the day after the earthquake. So that puts an immediate huge amount of pressure on the response teams. One, to bring back resources, but also to get emergency water supplies out to the public. And that bottom right-hand photo there, you can see some of the queues. Of course, when you have that much damage to the water supply and you've got that much damage to the wastewater supply, you've got big public health risk issues as well. Christchurch is quite unique that its water supply comes from under the ground and it's untreated. And so and we don't chlorinate, so that's an elevated risk in terms of public health in these conditions. We put immediate water restrictions in place. Not that people were thinking much about watering their gardens, but that was an immediate initiative. And we also looked at bringing a desalination plant in from Australia, particularly the east side of the city. The pressures over here got very low, very close to zero. And we lost some key infrastructure over here. So we looked at, we set up a desalination plant on the beach there as an emergency precaution. On the wastewater network, damage was worse. So basically, almost half the city had very poor flows in the wastewater network. And this was complicated further because a lot of those areas were in liquefiable soils, and the older pipes pulled apart or cracked, and they filled with liquefaction material. So silty type stuff, so you're getting this sort of debris in the pipes. And it was very difficult to even tell whether the sewers were flowing or not. So you can't assess the pipe network until you get that stuff out. So one of the first actions was to look at how we were going to get some sort of sanitary service back to about 40,000 homes in the city. It was interesting that many of the older people in the city were familiar with regimes from the Second World War and using your gardens and digging your own latrines. So there were all sorts of helpful advice coming in during those early response periods. The city brought in about 2,500 portaloos, and they were distributed into the high need areas, but of course that's not going to service 40,000 homes very well. And there's a number of social consequences that come with sort of these outdoor emergency responses. So from the September earthquake, we'd had response from social services that kids didn't like and women didn't like using these at night. There were some issues with you see the best and the worst of humankind during these events. And also portaloos can be a disease transmission path because you have so many people using them. So we needed a different type of solution, and we went for, we ordered 40,000 chemical toilets the day after the earthquake and 250 storage tanks, and set up a temporary network in the east side of the city. I might add the mayor, or the ex-mayor there, that's not one that's being used. He wasn't brave enough to do that. So, but that gave us a in-house solution that was distributed to the homes within 2 months of the February earthquake. And that included all the chemicals that go with that and collection systems. So quite a logistic exercise. With that much damage to the wastewater network, we obviously had a lot of sewage overflows around the place. Containing those overflows within the waterways in the city was a key health risk mitigation measure. So Christchurch is quite lucky that it's basically got two rivers, one that flows down here and one that flows in here, and a third one that's further up the coast here. And the overflows were directed into those watercourses. So that kept the wastewater overflows off private property and off the streets, so helped reduce the risk, but creates another challenge that in the stormwater sense that you've got to make sure that you don't get any breakout from those waterways, otherwise you've got a big public health issue. The wastewater treatment plant, Greg will talk more about this later on, but significant damage to the treatment plant. It did keep running throughout the process, throughout the earthquakes, not all the processes were running, and that was a godsend for the city. The city had built a ocean outfall discharge which discharged 3 kilometres off the shore, and that came into service just before the earthquakes. And so any wastewater that actually got to the plant was being discharged 3 kilometres off the coast. So again, that was help support public health initiatives to prevent disease transmission. Greg will talk a little bit about the individual damage on the plant. Wastewater overflows. So there's two big spikes here. February 23rd was when the main quake came through, and then we had one a bit smaller in June of the same year. So the day after the day after the earthquake, we had next to no wastewater getting to the treatment plant. and that was because of damage to major terminal pump stations. As soon as they started to come back on, the overflows reduced. But you can see there that it really took until about October of 2012 before we got the wastewater overflow discharges into the environment under control. And that was a major achievement in the response and early recovery for the city, because coming into summer it enabled the waterways to be used again for recreational purposes, both the beaches and the rivers. With an untreated water supply and that much damage to the wastewater system, it was really important that sort of boil water notices, you can't keep them going forever. And we also had intermittent power electricity supplies for the first 2 months in the east of the city, because the electricity network had undergone similar damage. And so a decision was made pretty quickly to chlorinate the east side of the city. Because the damage on the western side of the city wasn't so bad, we were able to isolate the two parts of the city because of the well network. We're able to do that in the city, and emergency chlorination units were set up at all the pump stations, the blue triangles there, across the eastern side of the city, and we set up an ongoing dosing regime there. And once that dosing regime was stable, the health authorities were happy for us to lift the boil water notice across the city. So again, that's a big thing for families, you know, not having to boil water that you have to drink and cook with all the time. And if your electricity's on and off, then you've got to buy gas, and you know, there's a whole lot of flow-on effects that come from these things that you often don't think about until you're put in the position of having to do it yourself. At the time of the earthquakes, I lived up in the hills here. Oh, sorry, over here somewhere. And we were between the epicenters of the two earthquakes, and I think we used our spa pool as a bath for the first 8 weeks afterwards. So you need a bit of chlorine to keep that in reasonable condition. Stormwater issues. So often the stormwater systems, particularly in drier climates like Christchurch, are the forgotten service. One of the things that we did very early on was we got the surveyors out on the stop banks of the Avon River, because the freeboard we had on the design of the stop banks was only about 400 mils. And after the September earthquake, we had seen some settlement of the stop banks. After the February earthquake, they dropped up to 600 mils in some spaces. So we lost all the freeboard. The next king tide would have overtopped the stop banks. So we had something like 10 weeks to raise 11 kilometres of stop bank to avoid that situation occurring. And as I said, this isn't the river anymore. This was an open sewer. So it was a really critical function to get done. Some of these, this is an old yachting club, so it gives you an idea. It wasn't common practice, well, it's not common practice in New Zealand to row to the yachting club to then get in your boat. So you can see the amount of land subsidence that's occurred there. This was a subdivision that was built in the early 2000s, and you can see the height of the emergency stop bank there. Again, that's sunk between 500 mils and a metre. So a whole lot of storm water issues, and they had wastewater issues going on there as well. And when the rain came, getting the runoff out of that area was an additional problem. So you soon become aware of stormwater issues in these circumstances when you get a bit of rain. Liquefaction creates liquefaction eject material, which is a sandy, silty substance, which when it dries out turns to a concrete-like substance in your streets. And this is a subdivision in the east side of the city. One of the major initiatives immediately after the earthquakes was to get this stuff off the streets. It creates a whole lot of problems. From road safety, you can't see where the holes and damage in the roads are, so you get voids created under the seal. You can imagine some of these photos. I think there's one here of a house in the top corner there. the floor's cracked inside that house and the eject material's actually come up in their living space. So with that eject material comes a whole lot of water as well. So the carpets are soaked, the house is damp, you've got sand everywhere. Just not a very pleasant experience. And people were still living in these premises. Student Army was formed by a group of students at the university, and they did a lot of volunteer work. We coordinated them with the contractors. We also had, because Christchurch has got a big farming hinterland around, the farmers got together and they formed the farmy army, and they brought their machines in and helped clear this material. For those of you who come from rural communities, farmers have a different way of doing things to city folk, and let's just say they took away a bit more material than just the liquefaction eject material, so they weren't too worried about fences and other bits and pieces as well. During the peak of the liquefaction removals, we removed about 500,000 tonnes of material from the city between the two big earthquakes. This facility had a disused landfill just on the northern edge of the city. We had one semi-trailer turning up every 30 seconds during the peak removal period. So you can imagine the strain that places. They have to drive through rural or urban areas to get to this tip site. It was running about 16, 17 hours a day. So you start to create a lot of community issues just around traffic, noise, and people not being able to sleep and those sort of things. Not directly tied up with the three waters, but transportation becomes a huge issue in these events. You've got repair crews that are trying to get around the city. You can see the sort of damage that occurred to the some roads and bridges. I think we had weight limitations on a lot of the bridges and speed limitations on a lot of the bridges around the cities. So that made getting around the city a lot more difficult. It's fair to say that driver behaviour deteriorated significantly after the earthquakes. People are stressed, they're tired, and you've got this ongoing shaking going on, and so driver behaviour became quite a health and safety risk for the repair crews, both in setting up traffic management and also working in that environment. So this is the diagram. There's some modelling that the Rebuild Alliance did. So we had a lot of damage on a lot of the bridges, some minor, some significant. Some bridges were almost rebuilt. You can't just take down a whole series of bridges in the city at once. So a whole lot of traffic modelling had to be done to assess the impacts of one-laning bridges for repairs or taking bridges out of service at any time to see what effect that was going to have on the whole city. The earthquake, the government red zoned, and by red zone, the government looked at the damaged ground and said, okay, it's not economic to rebuild on this ground. It just needs too much ground improvement work. We're not satisfied that the ground improvement work will give a stable enough solution for people to rebuild on and to put infrastructure back in. So they bought up about 10,000 properties in the city. And so when you translate 10,000 families, you've got to put them somewhere. Whilst the city had an urban development strategy that was quite well formed and it had growth areas marked, the infrastructure wasn't immediately available to those. So at the same time that we're trying to respond and recover, we also have to be thinking about where are we going to accelerate infrastructure development to enable new sections to be available for people to build on. So this puts a lot of financial pressure on a local government and central government organisation. During this initial phase, you get swamped with analysts from all sorts of directions, giving good advice. Sometimes working remotely and doing desktop calculations isn't terribly helpful to a response and recovery event. So there were some absurd figures that came out with regard to the number of houses that had to be built, the number of people we needed in the city, and it creates a lot of hysteria that was unnecessary. You know, the reality is these things sort of self-determine their own movement, and the commercial parties respond quite strongly to them. Having some areas already set aside for urban development and infrastructure plans in place to service some of those areas are filled up quite quickly. The emergency areas that the government accelerated approvals through for, a lot of those aren't taking off at all, and it's simply because it was 10,000 people that families were having to relocate, not half the city. So, you know, you don't need to make provision for 50,000 homes if you've only got 10 and then normal growth on top of that. So the city, since that period, has been able to slow some of the initial infrastructure investment required, which has been helpful for its finances. Oh, sorry, it's just a... so Duncan Gibb, I think, was a keynote speaker. So I worked quite closely with Duncan during the early stages of the recovery, and he would have talked about the alliance infrastructure model that was put in place after the February earthquake. So after the September earthquake, the damage estimate across the infrastructure was about 400 million. And so the repair at that phase, it was felt that that could be handled through more traditional contracting models like design and construction type models under a program management framework, and that was set up and was starting to operate when February hit. When the repair bill went from 400 million to 3.2 billion, there was a realisation that we actually needed to bring the civil engineering resources and design resources of New Zealand together into one organisation to make that happen. And that's really how SCIRT was formed. You've probably heard a bit about this, so I don't intend to reiterate that. Happy to answer any questions about that. Like all things formed in times of stress and with big budgets, you know, they did a lot of good, but there's certainly lessons to be learned from these models as well. On the to interface with the Alliance, a client interface model was set up, and so there were basically three clients: the Christchurch City Council, CERA, which was really central government, so it's Canterbury Earthquake Recovery Authority. It's gone out of existence now, it's been replaced by some other bodies. And New Zealand Transport Agency, which is a New Zealand government funded roading agency. So they, if you like, they were the three funders to the model, and Christchurch City had insurance behind its assets as a funding source as well. Established a client interface team, and one of the main components of that team was the asset management team, or technical, what do we call it, Dave? The
IST? The integrated services team?
Yeah. So it was basically a team of asset owners that looked after things like the technical standards, approval of projects, looking at payback on projects, application of new technology, those sort of things, and was really one of the key interfaces between the funding authorities and the Alliance. In these events, you never get given enough money to do what you'd like to do, or even to do what's needed, and so prioritisation systems are critically important. And as part of any resilience or emergency planning, I really recommend that people with those roles have a clear think about what would be the prioritisation process you'd apply in those sort of situations, because being able to implement those things straight away helps speed up the recovery process and eliminates a lot of unnecessary discussion. A lot of talk and a lot of papers written in emergency events about the capital cost of repair. Not so much is written about the operating costs, and they are significant. So these three graphs look at the number of jobs that were issued to the response agencies in the three waters. So we had one main contractor who was coordinating that called City Care. And at the start of these graphs, this level here is the business as usual level of number of jobs that were issued per week. And you can see we thought after, where's the water supply one's the easiest one to, oh that's that one. We thought after September, when we managed a peak of 150 jobs a week in the city, we were pretty clever. But when it got up over 300 or 400, that was significant. The number of water crews in the city normally was about 10, went to 150 after the February earthquake. So the work concentrates in the water sector initially. You'll see the wastewater one, which I'm just trying to have a look at which one that is. Far one. There's a longer curve before you get into the work, and part of that was because you have to assess the damage first. So some things are obvious, but until you actually start cleaning out the pipes and you can see what needs to be done, it's much harder to identify the jobs. And stormwater, there was some immediate response, and then again it's got a slower tail. We did quite a lot of ops cost modelling and used quite a bit of cost engineering resource. And again, I'd emphasise the value of doing this stuff as early as you can, even if the information's not perfect, because what it allows you to do is to give your governance structures indication of the pain to come. So this model here was looking at the pace of the skirt rebuild, and we were tracking additional operating costs in the three waters and roading across all the suburbs in Christchurch, and doing predictions on how long that would take place until the capital works brought the system back to a near business as usual approach. So the area between that's the business as usual inflated cost, and this is the rebuild investment. This space in here, the integration of that space, is the extra operating cost. So that's, there's a number of factors since this was originally done. The government cut back the amount of money that was going to be put into the infrastructure rebuild. There was a series of prioritisation events that took place which changed technical standards and have increased the legacy that's been left for the city. But Christchurch City spent about 440 million extra in operating costs since September 2010 just on the infrastructure. So it's a significant investment, puts significant pressure on the rating environment for the city, and you get nothing for it. Well, you get the service. Tied up with that is the contingent liabilities that are left after these types of events. You're not going to get enough money to return your asset base to where it was, unless you've got a very generous government or very generous insurers. And these three graphs illustrate this point quite well. So this is the age profile of one of the pipe networks. I can't remember what wastewater is it? Yep. Prior to the earthquakes in 10-year band ranges. That's immediately post the earthquakes, so you can shift. You can see the remaining life has shifted significantly to the left. This final graph is some modelling that Dave did for us and his team did on what the wastewater network would look like post the skirt rebuild. Now this graph was actually done prior to optimisation exercises, so it's actually not that peachy now. It's worse than that because not as much investment has taken place. I think, and this is a personal opinion, but I think it's a matter of principle and good governance. He who gets left with the legacy should decide how the legacy is created. So in a lot of the decision making around this was really forced on the council, and that its ability to influence how it repaired its network as the recovery progressed, was reduced. And that's going to cause quite a few problems in managing the asset base over the next 3 or 4 decades. So a few key points, I guess for me from the response side. Forging strong relationships in business as usual times is really important, and be that with your consultants or your contractors or your regulators or your health authorities. It pays in spades when the disaster hits. Resilience planning and resilience investment is good business. It's not gold plating. There's a lot of talk about resilience until people have to invest in it. Until you have business models and cost benefit models that actually value resilience, and to do that you need to have an NPV period sort of 20 to 30 years and take into account the consequences of natural disasters, then it is hard to get resilience investment to stack up in some cases. So sort of getting the right business models and business investment templates is important. You can't avoid risk, and risk management's not about avoiding risk. So a good understanding of risk and how to mitigate that is critical. Communication's really important. I've talked at a number of water conferences, and I say to the water managers there, if you aren't trained in media communications and you live in a earthquake prone area, might be a good idea, because if it happens you'll be in front of the cameras. Infrastructure needs to compete with social needs, so as Ian said to start with, it's not just a matter of your pipe's been broken, your house is broken, you've got insurance woes, community facilities are not there. At one stage in Christchurch there were no shopping malls on the east side of the city, so to go and get your groceries you had to drive in the ridiculous traffic over to the west side of the city to get your groceries to come back. So you're placing all these extra stresses in people's lives. And you need to focus on the outputs, not the inputs, so don't micromanage. Unfortunately, government bureaucracies, the longer they sit in recovery, they love to micromanage. And it's really counterproductive to a good recovery process. Okay, that's all from me. Thanks very much. Happy to answer any questions at the end. Just a few acknowledgements there.
Thanks, Mark. So I think my presentation is sort of going to fit in after Mark's and not quite cover my the top of my paper, which was about decision making around infrastructure. But I'm going to talk about damage investigation analysis, and that was in my role with SCIRT. So the damage assessment challenge, summed up best by Donald Rumsfeld. There were things we knew about, things that were obvious to us that we had to fix, and we knew there was items that we didn't know about that we had to research and investigate, but also these unknown unknowns, and they were things that popped up along the way. So a key part of an assessment process is to be flexible enough to respond to all those three sorts of things. Things you know you need to research, and the things that pop up along the way. So the obvious stuff is the damage that's visible, and Mark mentioned the first response efforts into water supply renewals. I mean, they were obvious breaks, often causing big fountains and roads. Those breaks were apparent, they were reported, and they were acted on pretty quickly. And the same with roads. There was a lot of make-safe works to get the roads working again and passable, to get silt removed. And so that was really the obvious damage that was seen. Other damage is hard to assess, and Mark mentioned also that this delay in responding to the gravity wastewater network and stormwater networks. And that was really because a lot of people left town, therefore the networks went under much pressure. There was breakages downstream as well, which meant that the services weren't in place. And so there wasn't a recognition that there was actually a whole lot of damage initially to below ground infrastructure. So this really brought a focus on this gravity pipe assessment. And for SCIRT, this made up over half of the actual rebuild cost. So it was the biggest thing in the rebuild, was about fixing broken gravity pipes. A huge expense, 1,600 kilometres of gravity wastewater, I think he mentioned 500 kilometres of that damaged. So a substantial portion of the gravity network was damaged and required repair. There were sort of three elements to that. The first was the immediate service response and getting service back on again. That was making sure the people actually had a service, a wastewater service. The second was doing assessments to check on functional damage and structural damage of the pipes, and that was really the focus that Scoot had initially. And then as the rebuild matured, there was a greater focus on levels of service. So recognising that we were moving into areas that weren't as badly damaged, could we be more efficient with our rebuild spend and focus on our spend on returning service to areas rather than just fixing damage. So in terms of traditional inspection methods, we initially started with the standard methods for functional assessment, and that was survey. So you surveyors, we had plenty of you guys out there doing this. Initially GPS survey across the city. We surveyed every single wastewater manhole. I think there's 50-odd thousand of them. And then we followed up with more detailed surveys. The problem we had through the rebuild phase was that we had ongoing earthquakes, and therefore we had to re-establish benchmarks and repeat surveys in some areas where the ground had continued to settle. So that was really a functional assessment of the wastewater network. The next was the structural assessment, and we did that through CCTV. And this is a closed circuit TV inspection, so putting little cameras down pipes. It's a traditional way of checking the condition of the pipe, but for Christchurch it became very expensive. It took a lot of resources. It took about half of the nation's CCTV resource was in Christchurch doing this thing. And probably about 5 times the cost that it normally would because of the amount of silt that was in these pipes and the high groundwater table and high flows we had to deal with. So that caused a problem for us in that we couldn't get enough inspection done at a rate that fed the rebuild. Scoot had a mandate to get the city back up and running again within 5 years, and that meant we had to start spending money at quite a rate on physical repairs. And so we had to, the challenge for us was that, given that the limitations around how fast we could assess damage, what other things could we do to assess damage, that were non-traditional. And so we started to investigate some other methods of assessment. The first was pole cameras. That seems pretty simple, but basically putting cameras on the end of poles and using that as a way to do a quick and dirty assessment of problem areas. And that became the routine way of assessing damage in stormwater pipes, where the assets were typically quite short and the pipe size quite large. So pole camera was a good tool. We developed a method for assessing the profile of the pipes, so that's how the grade of pipes varied between manholes. And that wasn't information you could readily collect from CCTV because of the nature of the damage. And so this was a technology we worked with a local contractor who was sort of familiar with doing geotech investigations, and we applied that to our pipe assessment, and that was a useful way to check the functional condition of pipes. And then we developed also a predictive tool. So we found that we developed a model, a desktop model that pulled together different factors that can influence damage, and use that tool to predict where damage would occur. And this was a way to really focus our inspection effort and to not spend a lot of money on inspection where it was very clear and the modelling could show us that the damage was such that the pipe required renewal. So rather than spending enormous amounts of money actually determining that, we were able to rely on the tool to tell us that there was a good chance the pipe was damaged beyond repair and therefore it required renewal. So that was we called that our PDAT, or our Pipe Damage Assessment Tool. And that allowed us to do a sample of CCTV across the city and then produce predictions of overall damage across the city. And that really led to us being able to forecast where we're heading with the rebuild from a cost point of view. And it meant we could focus our efforts on areas that were likely to be more damaged. So this is a plot of damage It's similar to what Mark had around service, actually, as it happens, but really focused on the central area. This is structural damage. There was additional functional damage in the western part of the city, eastern part of the city out towards the sea. Out here, where even though the pipes were quite new, the grade, the differential sediment and grade changes that occurred out here meant these pipes were also, from a functional point of view, very damaged. Whereas the main structural damage occurred around the older earthenware pipes within the main CBD area. And then obviously through a sample of CCTV and using our model, we were able to predict what damage was like in other areas. So, as I mentioned, we moved through the rebuild phase from a focus on repairing damage where we found it to a focus on returning levels of service. You know, we were limited by our rebuild budget. We couldn't afford to fix all the damage, so there's lots of damage that still exists in the network out there. And so the focus of our rebuild was really, from an inspection point of view, was to focus on measuring network performance and then targeting our rebuild effort to return levels of service. So these are some information we pulled together. This is public lateral maintenance, so this is how much effort was going in by the maintenance contractor to repair laterals. Those are the pipes that run from the house to the street. This is overall maintenance costs overall. So again, the high maintenance costs in the eastern part of the city. Infiltration, I&I, so that's where flows were substantially higher. We looked at that information, and then we pulled that together to a level of service score. So we used multi-criteria to develop a risk map, basically, that focused our efforts on rebuild. So lessons from this process. I think we invested heavily in GIS, and that became our main tool for both storing our data and being able to communicate that and make it available to designers, to asset owners, to contractors. So GIS has been a big part of it, and will continue to be a big part of the city's ongoing management of their assets. We put a big focus on, and I think having a greater focus, and probably for future events, on levels of service, knowing how your network operates current day, so that when you have an event, you can benchmark that and see what's happened. Data management systems were important, so the amount of data involved in cameraing pipes is huge. And every file was 300 megabyte, so it's a massive amount of data. And being able to manage that data in a cost-effective way is pretty important. So having some foresight about how you manage lots of data is pretty key. Having skilled workforces. We found that when we started our CCTV effort that the level of, the quality of the results that we were relying on was very variable. So the SCUD had to implement a whole training regime through their workforce to get everyone up to the same level of inspection, so that we could then rely on that data for our design. If we hadn't have done that, the data coming in wouldn't have been any good to us. Therefore, our decisions around rebuild would have been pretty hopeless. So, maintaining a skilled workforce is essential, and that's both condition assessment and rebuild. Maintaining flexibility, as I mentioned, we had to change tack through our rebuild process. Looking at other methods to assess pipes where the standard methods were too slow for us and too expensive. And then I mentioned this risk-based tool. I think that overlaps with the GIS, but being able to focus your efforts through a risk-based approach is a great way to be. I think it's a method that's being adopted through New Zealand now for councils to make them prepared for events, but also they're applying these tools also for their renewals planning as well. Thank you. So that's my short and sharp data assessment. I'll pass across to Amber, who will talk about more about the design focus.
Hi, so I'm going to briefly recap what the main bits of damage to our horizontal infrastructure was, and then work through how we investigated and came up with our design solutions, and then go through some specific design elements that we came up with. So as Mark and Dave have sort of illustrated, there was severe damage to the city's infrastructure. Some of the main ones would probably be the pipe breaks, lateral spread, buoyancy uplift and differential settlement, and rotation of the pipes. But in addition to this, there was severe land movement as well. Areas of the Port Hills had about 1/2 metre tectonic uplift, and areas around the Avon River, for example, experienced about 1 metre subsidence. And that obviously has severe implications for what was gravity networks. So to put that in perspective, this is Christchurch. Most of our stormwater system does drain via gravity into the Avon and the Heathcote rivers or to the estuary. And that's complex because in Christchurch we're relatively flat and low lying. In the east we've got a reduced level of about 15 metres and down below 10 metres in the east. And to put that in perspective, a mid-sea level is 9.3 and a 5-year high tide is 10.8. So we've immediately got an issue there for gravity drainage. Now, before the earthquakes, normally what would happen in, say, our stormwater system is the rain would rain, come down our gutters and along our land, and then it would be taken by our primary system through curb and channel, sumps, pipes, open channel swales, and some pump stations to discharge. And we also relied on a secondary system, which was overland flow over roads and reserves. After the earthquakes, basically, this happened. So the main challenges in there was broken and damaged pipes, silt ingress into those pipes, which caused blockages and reduced the capacity. The road drainage being impeded, sumps were no longer at the low points and our secondary flow paths were all disrupted or going in different directions. And then we had land settlement. So some properties were now lower than the road. They used to be able to drain to it. Entire areas were now lower in relation to the tide and could no longer drain via gravity. And any settlement is reducing the capacity of our gravity stormwater system. So, how did we go about repairing our networks? As Mark went through, firstly there was the emergency repairs, and then SCIRT set up. So SCIRT worked to first do the asset assessment to understand what the impact on our systems were, and then what was the criticality of that damage on our level of service of the network, and then we went in and designed the repair or renewal of those assets. It's worth noting that there were other organisations doing other work as well. So Council's Land Drainage Recovery Program was looking at land drainage as a larger catchment, looking at large catchments, land use, open channels, rivers and non-horizontal infrastructure that SCIRT was looking at. And then, as Mark mentioned, the CCC's normal capital programs were ongoing. The city wasn't standing still. We still had ongoing works. So it was really important that we shared our knowledge and shared the data and information that we were gathering. So we collected a whole lot of information, and once obtained, we displayed it all in the SCIRT GIS viewer, which was a way for us to, in a very accessible way, spatially show all of our information. To list a few asset sets that we had in there, we had all of the CC's GIS information. We had data from Environment Canterbury, LINZ, Port Hills Geotech Group, CityCare. We had geotech investigations. We had roading condition data, flood complaints, emergency repairs, existing design drawings, and operation and maintenance considerations. So there was a lot of information in there that everyone had access to. Another really important source was LIDAR. So Christchurch was lucky enough to have several sources of both pre and post-earthquake LIDAR, and from comparing those data sets we were able to establish what the ground movement was, identify the drainage paths and subcatchment boundaries, figure out where the low-lying areas of land were, and we used that for hydraulic modelling when that was needed as well. So once we started getting into all the work, Another really important thing was the creation of guidelines and standards. So SCIRT and the council work together on these, and they're ongoing information sources that are continuously getting updated as we learn more information. And it sort of sets the standard for survey, hydraulic modelling, damage assessment, and all of our specific design features that we've come up with. And again, another important thing just to facilitate all of that coordination and working efficiently was the use of similar software. So we had our GIS viewer, pipe damage assessment information was stored in Infonet, design information and survey information was in 12D, and we created a asset assessment spreadsheet which was a link to all of these different data sources within SCIRT. This sort of systems are still being developed. I was at a SCIRT meeting 3 weeks ago, and the IT department there stepped up and introduced us to, they've made an app on their smartphones so that the contractors and the surveyors can step out on site and pick up as-built information in the field, upload that straight into the council's asset database for verification, and it just makes that whole process more quicker, more efficient, and it's so much easier to record information when you're standing right in front of the source. So it's really cool to see that these devices are still being created. So, the design itself. The focus for SCIRT design was on resilience. We considered what sort of damage could happen to our horizontal infrastructure, and was there a way that we could stop this damage from happening, or how can we fix it when it does happen? So in a lot of places we have moved our design thinking from trying to make things unbreakable, because that's pretty hard and very expensive, to instead making things easily repairable, and that's repairable safely and cost effectively. So this created a few new ways of doing things here in Christchurch. One aspect was the use of flexible pipe materials. So for the wastewater system, this meant use of PE and PVC pipe. However, for stormwater, because reinforced concrete pipe did perform okay, it's still used often, it's very cost efficient, but in areas with critical infrastructure or those with a very high risk of lateral spread, PE was often used. This is an example of a very large diameter culvert underneath a new causeway. So here PE was chosen as the pipe material because of its flexibility and durability. Another design use was the use of trenchless pipe repair methods, so things like COPP lining and spiral bound lining. So these repairs are often more cost efficient than digging up the road and installing a new pipe, and it means that we're not causing that amount of disruption to the road and no trenching. Then, when we're looking at the pipe network itself, SCIRT started steepening up pipe grades. We used what we call the tractive force method, which is instead of just setting a minimum grade for your pipe, we worked to ensure that we were achieving minimum shear forces that keep the wastewater flowing down your pipe. This meant that in places we were forming sub-catchments in our network, and we needed new pumping stations. So again, SCIRT they pioneered a new lift station design, which instead of installing a brand new pump station at the site, it just simply using a small proprietary pump lifts the sewage back up into a higher pipeline. There are a few other easy quick wins. Reducing the depth of sewers where we can means that they're more easily repairable in the future. And in places we started using collector sewers alongside the main trunks just to keep that pipeline higher. We also investigated alternative systems to gravity, and to justify that, again, we did a lot of multi-criteria analysis, net present value calculations, and a lot of community consultation. And coming out of that, there has been installed around 10,000 pressure units into Christchurch and about 4,000 vacuum sewer units. Now, pump stations. We had sort of four main things, and that's related to the four main damage types that we wanted to incorporate into pump station design. We want to improve the slope stability and reduce the lateral spreading. We want to limit differential settlement. We want to limit buoyancy uplift. And we want to make the entire pump station structure, its valve chambers and its inlet and outlet pipes, one compatible system to stop those pipe breaks and shears and discontinuation of services at the interfaces. So the key considerations to do this was firstly site location. Sometimes we didn't have a choice, but if you could pick a better, more stable ground site, that's a good start. Ground improvement or piles, and this would be both beneath the pump station, around it, and around those critical inlet and outlet pipes. And we also tried to have a consistency in the foundation and performance of our ground improvement. For buoyancy, a couple of extra things. You have to relieve your poor water pressures that are always a problem but become more of a problem during a liquefaction event. You can install tension piles or anchors to help with that, and you can also add extra weight to your structure or have an extended base on it just to keep those structures on the ground. And then for keeping the entire site compatible, other simple things we could do, like over-steeping inlet gravity pipes, using those flexible pipe materials or flexible pipe connections, and providing slack in any service connections so that they can move a bit. We're also thinking of our site layout, making access and maintenance easy because of the layout, keeping things shallow so that it's easier to dig down to, and considering how, if another serious event does happen, how can we re-level, how can we fix things? So as a couple of examples, I've got a couple of photos up there of pump station 136, which is a new pump station in the east. It takes about 1/6 of the city's sewage. You can see here the foundations and the ground improvements of underneath that station. So it used continuous flight auger columns of about 20 MPa concrete that was installed beneath and around the pump station. So these limit the liquefaction, and there's also a flange base on that pump station and granular backfill to provide that lateral support and resist the buoyancy uplift. You'll notice that the columns underneath the structure and underneath the pipes taper out. They decrease with depth as you go along, and this is to provide that continuity between the inlet and the outlet and hopefully limit any shear failures of those inlet pipes. The other example there is a stormwater pump station, 229. So this is a bit different. Here, one of the key features of a stormwater pump station is that the overland stormwater needs to be able to get into that station. So if the ground settles, you want the pump station to settle as well. So that rules out ground improvement or piles in this case. So here, the pump station was founded on a gravel raft, and that will resist buoyancy uplift and any differential settlement, and hopefully it will allow that pump station to settle with the earth if that happens. Here it was also really important to keep the whole thing shallow to resist that buoyancy uplift and to make future repairs on the pipe or the pump station easier. So I guess my few conclusions were it was really important right from the start, the efficient asset assessment was really key, just to know what we were dealing with, know what we had to design for. And then coming up with those guidance documents and standard details made the simple stuff easy for us and improved our collective quality of work. But always on every single design we had to be thinking, for this specific design, how can I get value into our repairs and renewals? How can I make this design resilient? What's special about this one? And then finally, we needed to share all these lessons learnt, both amongst ourselves and everyone else, so that we know why we designed things the way we did. And now I'll hand you over to Greg.
Thanks, Amber. Okay, you've heard about the network. You've heard about the stormwater, you've heard about the wastewater, and all the work that was done extensively for a period of time after the earthquake. So I'm just going to give you a few highlights about the wastewater treatment plant. There's only one wastewater treatment plant in Christchurch, and it's treating the flow from the whole city, so that's about 250,000 cubic metres of wastewater a day for a population of about 360,000 people. So obviously it was crucial that plant was brought back online after the earthquakes as quickly as possible. The treatment plant really has three main components. So there's the treatment plant itself, there is a 220 hectare area of oxidation ponds, and then there's an ocean outfall with a big pump station. So there are really three main components, and some of the issues around resilience and how resilient the plant was are linked to the fact that there were three different parts and we could rely on those different parts at different times. Okay, a bit of background. We've talked about liquefaction quite a bit, but I thought we could break it down to the basics to help get an understanding of it, because it was particularly important at the treatment plant site. So because the plant is in a coastal location, it is built on deep sands and with very shallow groundwater. So those two things in combination make it highly vulnerable to liquefaction. What happens in a liquefaction event is, with that force being applied, the soil is liquefied, and when it's liquefied, the weight of the soil sitting on the groundwater creates these tremendous pore pressures underneath the ground, and that's what causes the damage. The interesting thing for us at the treatment plant was some of the assets are built on top of the ground, other ones are built below the ground. So the damage profile we experienced at the treatment plant was strongly related to the height of those assets and whether the bottom of the asset was below the groundwater level or not. Okay, so I mentioned that the impact had to do with different structures. Deeper structures, much more serious damage, lighter, higher structures, less damage, and things sitting on the top of the ground were still damaged, but generally to a much lesser extent. Okay, just a collage there of the sorts of damage issues, and they're similar to the photographs you've seen of problems throughout the network. So we've got differential settlement happening on land at the treatment plant site, we've got extensive cracking of concrete structures. The top right hand corner, that's the inside of a clarifier, which I'll talk about a bit more in a minute. So these are very large buried concrete structures with concrete floors that were severely damaged. And then on the oxidation ponds, those lower photographs, these oxidation ponds have extensive earth embankments. What happens to an embankment if you get liquefaction underneath it is the support structure for the embankment basically ceases to function and the whole thing spreads out and settles. So you get a lot of change in height, and that creates a problem for the embankment as a water storage device, and you get lateral spreading, as Amber mentioned, all this cracking, and the whole thing starts to fall apart. Where you've got civil structures built into those embankments, they get quite seriously damaged because of all the massive amount of movement that's going on. The ground and the embankment's pulling a pipe down if that's attached to a structure in the pond that wants to go up. So you get all sorts of untoward differential movements. So what happened after the earthquakes? In the initial week or so, the plant actually received very little load. So the wastewater network was so severely damaged, and also the power was off. So because all of the wastewater is pumped to the plant, no power means no flow, nothing arrived. So there was damage, and I think there was the beginning of the repairs, but really the worst of the problems were yet to come when the network came back on. So that top section is showing that we had multiple stages in the process. Before the earthquake and after the earthquake, we had levels of damage within individual process units which took those process units out. But nevertheless, because of the flexibility of the plant and the opportunity to share those loads to different unit operations, we could adapt to that and get the plant back up and running fairly quickly. Okay, sand. So you saw the pictures of that sand mountain, and the network is built in sand, and of course with all that damage, cracks and pipes, huge amounts of sand got into the network, and it really only started arriving at the plant when the network came back online, probably starting a week after that 22nd of February earthquake. So we're talking about massive quantities of sand being pumped to the treatment plant over a period of months, thousands of cubic metres. That photograph on the right shows a guy cleaning out a digester. The total volume of the digester is 5,000 cubic metres, and we removed 4,800 cubic metres of sand from it. So these tanks were literally filled up to the top. And once you've got a digester full of sand, it's a major exercise to clean it out. Trickling filters, so I talked a bit about this. The trickling filters had shallow foundations. They kept on operating continuously throughout the earthquake sequence, and that was great because they became the core of the treatment process. Ultimately that became a problem though, because for insurance assessments you have to take these assets offline, get inside them and do a whole lot of assessment work, and that was difficult to do because the plant was totally reliant on them maintaining operation 24/7. Clarifiers, so downstream of the trickling filters we've got these clarifiers. What they do is they separate out the solids from the treated wastewater before it's discharged to the oxidation ponds, and these were seriously damaged for the reason that I explained. It's all about liquefaction. You get these tremendous pore pressures under the floor. What happened was the whole floor just popped up. The worst case scenario, we had about 900 millimetres of uplift in the concrete, so we had to basically build extensive new heavily reinforced concrete floors inside these structures. There's a lot of survey work involved in that because the water flows through the clarifiers by gravity, so all the levels had to be very accurately re-established. So, yeah. Amber talked about cure-in-place liners, so we're using similar techniques at the treatment plant as necessary for buried assets that can't easily be removed, to put liners in large bore concrete pipes that were damaged. So what were the lessons learned? Just a couple of things. The first one is about flexibility. So if you're designing an infrastructure asset, you need to do critical analysis around which are the critical parts and what are you going to do in a major incident like an earthquake. We were very lucky at Christchurch Wastewater Treatment Plant because there are multiple stages in the process, and within each stage there's also quite a lot of redundancy. So even with partial loss of service in some parts, the whole of the plant continued to operate at a level. Another theme, layers of protection. So Mark talked about public health risk. You've got the network, as the idea is to take away that wastewater and treat it to maintain public health. We did not have any serious disease outbreak in Christchurch City after the earthquakes. And one factor in that was these layers of protection. So even with minimal treatment being provided at the treatment plant, you've got another level of protection in the oxidation ponds, and then you've got another level of protection through this outfall, which is pumping the wastewater out to sea. So layers or levels of protection. Third item is about risk management. It's hard to conceive of all of the adverse scenarios that might arise when you're designing an asset, particularly if it's a very low probability but high consequence event, and engineers are put in situations where budgets are constrained. So you need a rigorous approach to designing critical infrastructure assets which takes account of these risks, because once they're built, it's very, very hard to retrofit earthquake resilience. And the last one really is around insurance, which we haven't talked about. So I doubt that the people at the council had read the fine print of their insurance policies much before the earthquakes, but I can tell you they started reading it the day afterwards. Insurance resolution has been a very long, complicated process, and I think we've learned a lot. You have to assume a litigious approach for everything from day one, and there's a whole lot of things you need to do beforehand. Critical to have very good understanding of the asset condition before an event, because what will tend to happen is there'll be arguments around if there are cracks in a structure, an assessor will say that they were existing before the earthquake, and you get these types of arguments all the time. So having good understanding of the asset prior is crucial. The other thing as engineers is that we want to get hands-on and start fixing things, particularly at a time where it's so important to the community. But you've got to stop yourself from doing that, and you've got to do proper assessments. Otherwise there can be problems later. Nevertheless, you're going to end up in a situation where you are forced to start doing repairs for the good of the community before the insurance matter has been resolved. So councils find themselves in situations where they are expending large sums of money and with no guarantee of recovering that for a long period of time. So that's just a risk which councils face. That's the end of my talk. But that's the end of all of our talks. Thank you.
I'm Wally Sanford from Cromwell. There was a mention of earthenware pipes being in the older part of town that had some problems, but did you learn anything about perhaps pipe materials or jointing or backfill that caused problems that probably could have been avoided in some situations?
I can answer that one, I suppose. I mean, we certainly found that that earthenware pipes did perform the worst from a structural point of view. We have lapels. Thank you, Ian. The relatively new PVC pipes perform well, and they have been a feature of the rebuild. So for gravity pipes, PVC pipes are still being used. Large diameter concrete pipes are still being used by the city. We tried to calibrate it against, because there have been different methods of backfilling pipes and laying pipes over time in Christchurch, and it was difficult to get a trend. And it's because the ground is so variable. So we found the predominant driver for damage was actually pipe material above any other factor.